Again. So, yeah, there are different numbers depending on what your instructor says. So, the most important thing is to learn what your instructor says to learn, right? And to learn what your instructor says is not necessarily what the book says. I used to study from the book, but I quickly gave that up because, to be successful, and I wanted to learn everything in the book. That is how I define success. But then I changed. I changed to I wanted to learn everything that the instructor said to learn, right? And then ignore some of the other stuff because you quickly become overwhelmed. There's just too much information in the book. Not enough to get in 10 weeks in a quarter at UCLA. And so if the instructor says there's 5 types of chemical reactions you need to learn, then you learn those. You don't. They have their reasons because the classification scheme, there's no right way or wrong way. Everybody has their own kind of classification scheme that they develop, and there's arguments for that. So Petrucci has his. So Petrucci has his classification scheme. And, in Petrucci you got combustion, you got precipitation, you got acid-base, neutralization, etc. And so you count all those up and you get a lot. But other books, actually not General Chem, but other more advanced books in synthesis will break it down into fewer categories. For example, combustion reactions share a lot of similar characteristics, let's say, as redox. In fact, they are redox reactions, so why not just group them as redox? And so to keep life simpler for you guys, I think it's easier to have fewer categories than more categories, and then subdividing. Well, what kind of redox is that, And so I have a lot of Chem 1A former students, and so there are three basic types of chemical reactions. There are some reactions that are a little different, which we'll talk about in these PowerPoints. Why do we want to know the types of chemical reactions? This is not. I'll have to adjust that. Because we want to know chemical properties. A lot of you, physical properties, no problem, but chemical properties, we want a very good understanding because we want to know how things react. What happens when you mix things together. So this is when I was working in chemistry. This is what I was doing when I was at UCLA, when I was at UCSB. This is a goal. The goal is understanding nature, and to understand nature, you need to see how the properties depend on what? Well, what do the properties depend on? Both physical and chemical properties. Well, they depend on composition and structure. And so during my whole time at UCSB doing my PhD research, trying to understand, what was the underlying composition, what was the underlying structure that gave these properties. And so what our whole research group was after, and people were working on different things, were something called waveguides or fiber optic cables. Fiber optic cables transmit light. But the problem is, pretty soon, when you hit a certain wavelength of light, that wavelength gets absorbed by the cable itself. And so what I wanted to do is increase the optical window, the transparency of the cable to very long wavelength. And so, what types of compositions, what types of structures don't absorb very long wavelength light, like infrared? And most things absorb infrared light because infrared causes what to happen? A lot of matter absorbs infrared because infrared light causes what to happen? They use infrared lamps to do what? Heat, right? And so they cause vibrations, heat, basically. And so just wanted to look at that. And so basically we want to be able to correlate these things. So when we look at chemical reactions, obviously we look at the composition, and then oftentimes we'll look even deeper at the structure. For example, the composition of diamond and graphite are the same, but their chemical reactivity is totally different, right? Why? It's because of structure. And so we want to look at these in depth. This interrelationship here, composition, structure, and properties. And so how do we approach this? Well, we use a mix of theory and descriptive chemistry. And so what is descriptive chemistry? Well, the way I define descriptive chemistry is just factual knowledge. You know, you do an experiment, you observe what happens, now that's part of facts of nature. And so descriptive chemistry is just what we call memorization, you know, memorizing a whole bunch of facts. You know, does water burn? Does it? Does CO2 burn? You know, I don't know. Maybe you've observed it, maybe you haven't. But, you know, to think about CO2, well, you know, I guess I could try to burn CO2 and see what happens. But we don't want to have to memorize everything, do you? And so we want to be able to supplement some of our memorized facts, that is this descriptive chemistry, with theoretical knowledge. And so rather than doing an experiment to determine if CO2 burns, we can use a little bit of theory to figure out, you know, does it make sense that CO2 burns or not? And so our approach is two-pronged, but we don't want to use theory for everything because theory can be too much work. And so, for example, do you want to use theory to say, you know, why doesn't water burn? You know, prove it to me theoretically using physics and math. Do you want to do that? No, you just say, it doesn't burn. You try to burn it, it doesn't burn, right? It's a fact of nature. Something like that. If you tried to combust it, let's say. It's not a good fuel. Maybe you could eventually get it to combust, right? And in fact, you could, but and so there are some things that are better answered with theory. There are some things better answered just by having factual knowledge, you know, being exposed to this stuff and just remembering it, you know, repeated. And so that's why we have this two-pronged approach. It's a mix of theory and descriptive chemistry. And so here, is HCl a gas, liquid, or solid at room temperature? What do you want to use? Do you want to use a theory, physics, electrical interactions? No, you just want to say, yeah, HCl is a gas. Why? Because that's what I was taught, right? Or that's what my experience is. You can smell it. You ever smell HCl solution? Well, each substance, you know, has a unique set of chemical and physical properties that arise from its composition and structure. And so often we do this. When we're trying to identify an unknown substance, let's say I had a beaker. Let's say I had a beaker of clear, colorless liquid. We call this a CCl, for clear, colorless liquid. We have a whole bunch of abbreviations. You could look those up online. Have you ever heard of CCS? Clear, colorless solution. This could be a CCS or CCl, I don't know. Usually an L implies it's pure, whereas an S would imply it's a mixture. And so do I know if this is a homogeneous? Yeah, it is homogeneous, but do I know if it's a homogeneous mixture or a homogeneous substance? I don't know. Well, how could I figure it out? You know, if somebody told me this were pure water, how could you prove this? How do you prove it? Before you drank this, what would you want to do? You want to test it. You know, we know that pure water has certain properties, right? And let's say if this stuff here boiled at about 100 degrees C. Is that enough? No. Well, it depends. It depends on what you need to do with it, right? To drink it, you probably say not enough. You want more verification. And so traditionally in chemistry, we use these properties to identify, substances. This is their fingerprint, so you can say. But we have even more sophisticated tools, that we could use to identify this. Like how it interacts with light. For example, water has 3 types of vibrations it does when it absorbs infrared, and it absorbs quite a bit of infrared. Or how it interacts with other things. So we test it here. And so this is the example here. The liquid is clear and colorless. Well, that's some properties, but not enough. The substance is a gas, substance is green, yellow. If it's clear and colorless, what liquid is it? Who knows? It could be a whole bunch of different ones, right? If it's a gas, well, again. But if it's a green, yellow, corrosive gas with a boiling point of something, then you're probably thinking, what? Green, yellow, corrosive gas. Do you know any green, yellow, corrosive gases? Chlorine. So the first thing that would pop in my mind is chlorine, right? And so you want some facts memorized. Like when I was in Santa Barbara, there was a tanker truck crash there. A whole bunch of acid spilled out. And the TV announcer was saying, oh, there's been a huge hydrochloric acid spill. But the problem with that was brown fumes were coming off. Just these red-brown fumes coming off. And then you're thinking, does hydrochloric acid give off brown, red fumes? No. That was likely well, bromine does give plenty of brown fumes, but it was marked acid, so it had to be an acid. Bromine's not an acid. Bromine is what? If somebody asks you, what is bromine? Is it an acid? Is it a base? What is it? What is bromine? Well, bromine's a liquid at room temperature. It's brown, red, orange. Those are some of the physical characteristics, but what about the chemical properties of bromine? Can you tell me some of the chemical properties of bromine? What chemical property stands out with bromine? The first chemical property that comes to mind with bromine. Now you go back through your database and you think, okay, what are the chemical properties of bromine? This exact type of question hit me when I was a student at UCLA. I had one oral exam at UCLA, and that one oral exam, they asked me, what are the chemical properties of phosphate? And so, like you, I started to think, I was thinking there are lots of different properties. So I was thinking, well, phosphate, then I was thinking, I was trying to think of all the reactions phosphate would react with, And so it was like 3 minutes. Each minute goes by, because you're the only person that's supposed to be talking, so it's dead silent. And I'm trying to think of all the things that phosphate reacts with. And I thought I bombed that test because I couldn't come up with a good. I just said, well, they use sodium phosphate in detergents. You could react it with magnesium and form a precipitate. Just coming out with random reaction. Does phosphate react with sodium hydroxide? This is what I'm thinking. Does phosphate react with sodium hydroxide? Does it react with HCl? Does it react with this? Does it react with that? Then I thought, boy, my understanding of chemical reactions sucks. It's bad. And I'm a chemistry major. And then I thought, I went back through the book and looked at it, and then I saw, oh yeah, there are 5 different types, but those different types of reactions or 6 or whatever, depends on the book. They didn't help me answer that question at all, knowing that at all. And so anyway, going back to this, like for example, if I went back, what are the chemical properties of HCl? Do you guys remember this question from Chem 1A? Did I give it? I don't remember. It's a strong acid. Is that it? No. This is a strong acid. This is an oxidizer. It's a precipitating agent. What does it precipitate with? Silver, lead, and mercury. Silver, lead 2, and mercury 1. And so, you know, to have that, to that understanding to a point, you know, where you don't have to sit there and think 30 minutes. You think, oh, there are 3 types of reactions. Phosphate, what can it do? Well, it's a base. One thing, it can accept protons. 2, it can precipitate with everything except group 1 and ammonium cations, right? 3, if it's going to do anything, it's going to be a blank in redox reactions. Well, if it's going to do anything, it's going to be a oxidizer in redox reactions, because you look at the oxidation state of phosphorus, but it's not a very good oxidizer, otherwise you'd see it on the redox chart, right? And so there are a lot of things you could do now just by categorizing things a little more simply than what they did. And so now, you know, after that, because I felt so unprepared, so after that, you know, it's been bugging me for a long time. So, you know, now if they gave that question to me, no problem. It would be so easy to answer, but, you know, yeah, after that. But I'm thinking, why don't they do this in general chem? Why do I have to get a PhD to figure it all out? Well, you don't. You know, it's not that complicated, actually. And so this is just some more repetition. And this is what I was getting to. What are the properties of HCl? Do you know them? Can you listen? There are 3 chemical properties. There's the acid-base properties of HCl. H plus is a great acid. Chloride is a rotten base. There's the metathesis, what I call metathesis of double replacement. You know, it's going to precipitate out with silver ions, lead, 2, mercury. And then there's the redox. H plus is a moderate oxidizer. Chloride is a very bad reducer. So I went through Petrucci and looked at the types of reactions. Combination, decomposition, acid-base, single replacement, double replacement, combustion, precipitation. So far that's 1, 2, 3, 4, 5, 6, 7, and more. Question? No. All right. So, you know, what's the difference? What's the difference? How do we categorize? What do we look for? Usually, you look for patterns, right? Reactivity. But there are problems with this list. One, it's not very comprehensive. So, what if we're given something like this: HCl plus HNO3 plus gold? You know, this is a very famous reaction. Do you know what this reaction is? Or do you know what this is called, HCl and HNO3? This is a very famous reaction because this reaction will dissolve gold. And so this HCl and HNO3 mixture is called aqua regia, or royal water. It's called royal water because it dissolves. Well, how does it dissolve gold? You tell me. What type of reaction is this? Well, it's a combination. This is a combination of redox with the nitric acid. Nitric acid is a very special acid called an oxidizing acid. And HCl, there's one more property of HCl in acid base. Chloride turns out to be a rotten Bronsted base, but it turns out to be a decent Lewis base, which we'll talk about. And so chloride actually ends up attacking the gold as a base, Lewis base. And so it actually works, and you can dissolve the gold, solid gold, with aqua regia. Not that you want to test this yourself, because unless you can reverse the reaction. Okay. Also, it's confusing. Like, what kind of reaction is this? Well, tell me what does that look like to you? It looks like a combination reaction. You know, you take something, combine it with something else, and you form this new thing. What does this one look like? A combination reaction, right? And so in Chem 4, they have so many subcategories of combination reaction. There's the element plus element combination. There's the element plus compound, the compound plus compound. Did you guys memorize all those in Chem 4? You're supposed to have memorized all those patterns, right? And they're all different. right? But yeah, okay, these are both combination, but this one is totally different. This is a redox. This is a acid base. They're totally different. And so you don't want to mix them. You don't want to call them both the same, because it just confuses things. And then you don't want to have all these subcategories of combination reactions that you have to memorize in Chem 4, which we were just redoing the list for Chem 4 memorization, but not into it. And so the three basic types, why? Because they're three basic driving forces for chemical reactions in nature. And so each type has its own driving force, and all the metathesis reactions have the exact same driving force. Same thing with acid-base, same thing with oxidation reduction. And so three basic types because of three basic driving forces. So you have these on the PowerPoint. And so going back to this, does single replacement and double replacement have the same driving force?
Yes.
No. Single replacement is a redox. Double replacement is a metathesis. So these two are totally different driving forces, and yet every time I've taught Chem 1A, people get them mixed up. They think single replacement and double replacement have the same, like gas formation, that type of driving force. This is refreshing. And so the driving force is, what is a driving force? The driving force is typically, this is the way we look at it thermodynamically. Thermodynamically looks at energetics. And so the way we look at it thermodynamically is we're trying to form more stable products from less stable reactants. So what dictates stability? Well, typically something's stable if it has strong bonds. Strong bonds. Strong bonds is harder to break apart. It's more stable. As far as descriptive, well, what types of things have strong bonds? Like, for example, do strong acids have strong bonds? Strong? How about weak acids? Do weak acids have strong bonds? Yes, they have stronger bonds than strong acids. And so rather than looking at this, there's really just one driving force, But having to analyze everything becomes more cumbersome. So we have simple descriptive cues, simple descriptive things we memorize. So what types of things have strong bonds? Well, actually, I left this blank. Precipitates have strong bonds, right? You're getting the ions, they're in solution, and all of a sudden they come together and bond and precipitate out of solution. And so precipitation is something. Right? But precipitation, does it work for everything? No, it doesn't. Precipitation doesn't work for everything because that's assuming you have a magnesium ion here and a phosphate ion here, right? And when they come together and bond, it still stays as a magnesium ion and a phosphate ion. In some reactions, the actual identity of the element changes. So, for example, you might have sodium, the element, and sodium, the ion. If somebody asks you, okay, what was your sodium intake? Oh, wow, I don't have enough sodium intake for today. I need to supplement that. And so let's say you ran out of table salt, but you have a container of sodium metal. Would you take the sodium metal instead of that? No, you wouldn't, because they're different, right? And so that type of reaction is a redox reaction, and that has a different driving force because the actual, what we call oxidation state, or the property of that particular atom has changed. And so we'll look at these in descriptive terms now. So let's subcategorize these. For metathesis reactions, we have double replacement. Double replacement is the most common metathesis reaction you have. And metathesis is a name given to what? How would you describe what a metathesis reaction is for Chem 1A people? Yeah, ion combinations. You're just combining ions and you're coming up with a... So why do I call it metathesis? Why don't I just leave it as double replacement? Because that's what double replacement reactions are. You're looking for stable ion combinations by switching partners and seeing does it react or not. And the reason I call it metathesis instead of is because not everything falls into the double replacement pattern. The double replacement pattern is AB plus CD. And so we want to be able to tackle things that are outside that pattern, but still the same type of thing, just looking for favorable ion combinations. For acid-base reactions, we have your basic neutralization, titration, but we have others as well. For redox, we have single replacement, combustion, etc. And so this is a comparison with previous classification if you want to fill that out. And so all this just to predict potential chemical reactions between substances. And so here are the subcategory. For acid-base, we're going to primarily focus on Bronsted, Lowry, and Lewis. For redox, we're going to look at, actually I might skip single replacement. We're going to look at something called skeleton redox balancing, which you did in chapter 5, and the redox chart method, and other techniques like element plus element combination. Metathesis are just ion combinations and double replacement. When we predict these reactions, we have some basic assumptions. And one of the basic assumptions is the concentrations are fairly high, 1 molar. And the gases are fairly high pressure, 1 atmosphere. Extremely low or extremely high concentration can mean alternate reactions might occur. And so you aren't guaranteed, but this is useful. Even though you might be wrong, this is still useful because you can get an idea of what might form. Okay. And so here's an example of a double replacement reaction. HCl plus, what is HCl? Hydrochloric acid and AgNO3, silver nitrate. So hydrochloric acid and silver nitrate, the double replacement is going to precipitate out silver chloride and nitric acid. So HCl, one of the chemical properties, this is not an acid-base neutralization, is it? This is a precipitation. And so one of the chemical properties is it precipitates out like silver, lead, and mercury. Well, okay, we precipitate out that, but you could be mixing this and nothing happens. You're getting no precipitate. Why? Because if your concentrations are very dilute, nothing happens. You need a certain concentration. In fact, you need at least 1 milligram of precipitate to see it with your naked eye. And so if you're forming very, very minute quantities, you might not see anything happen. It looks like no reaction. Maybe there is no reaction. And so at very, very dilute concentrations, there is no reaction occurring. This reaction, silver chloride plus HNO3, well, the driving force for this is the formation of the stable precipitate silver chloride. The bonds are strong there. Over here, what is the driving force? So what would we form? Well, we take silver chloride and react with nitric acid, the reverse of this. We'd form silver nitrate. Silver nitrate is not going to precipitate. And what else do you look for in double replacement reactions? You look for precipitation, gas formation, and stronger acid to weaker acid. So silver nitrate's not a gas, nor is it a weaker acid. So we're going from silver chloride to nitric gives us silver nitrate and hydrochloric acid. Well, what's a stronger acid, hydrochloric acid or nitric acid? They're equally strong in water because of the leveling effect. Are you guys familiar with the leveling effect of strong acids? Strong acids in solution are the same strength, basically. And so, in other words, there's no driving force for this. If there's no driving force, we expect no reaction. But, did you know? Silver chloride will dissolve in hot, concentrated nitric acid. No problem. It'll dissolve. And so, it doesn't form these products, though. It forms a different set of products here. In hot concentrated nitric. Oops, I screwed this up. That's all right. There are plus other, right? Actually, you don't have this. I'll fix it later. Plus other stuff, because nitric reacts in a special way. Nitric we call a oxidizing acid, whereas HCl we call a mineral acid because of some of the redox characteristics of it. Okay, then we look at this reaction. You know, if we take lead-2 nitrate and sodium hydroxide, you know, we'll form a precipitated lead-2 chloride. But if we add too much sodium hydroxide, we form this. This is what we call like a non-stoichiometric compound. If you look at it, you know, how many hydroxides do we need for every lead-2? If I have a lead-2 plus, hydroxide's a -1, I'll need 2 hydroxides for every lead. But in this case, I actually have 3 hydroxides for 1 lead, which means I have an extra negative charge. This is what we call a complex ion. I got too many hydroxides stuck on there. It's because of the way it reacts. Hydroxide just attacks it and surrounds it, and we form this. So if I add too much hydroxide, the lead won't precipitate. It actually stays dissolved in solution. I actually did this reaction in Chem 1A, where I formed the white PPT and then just kept adding hydroxide, and the white PPT disappeared. You guys remember that? Yeah. You might have done it too, experiment 17, white PPT that disappeared. So, you know, if we keep our basic assumption, 1 molar in 1 atmosphere, then these rules are applied. But what do you do when you deviate from these? What happens when you deviate far from 1 molar? How can you make these predictions? Now, these are what we call qualitative predictions. In Chem 1B, this is one of the tools you're going to acquire this semester, is we're going to do more quantitative predictions. Rather than talking about the driving force of precipitate formation, stronger acid to weaker acid, stronger oxidizer to weaker oxidizer, you know? Rather than talking about the driving force in that way, we're going to look at the driving force in detail. And we're going to look at the thermodynamic driving force for this. And with that, this will allow us to make predictions. Like, say, we're at 0.1 molar. How is that going to impact things? We can do a calculation to figure out what's going to happen. And so this semester, we're getting away from the Chem 1A qualitative, and we're going to be doing more quantitative. What exactly is the driving force? Is the driving force like a semi-truck coming down, or is the driving force like a trickle of water flowing down the street? You know, what is the driving force? And so this is what we're going to deal with in thermodynamics part 2. But thermodynamics doesn't tell us the whole story. There still might not be a reaction. There still might not be a reaction because we need to also understand something called the kinetics. So, for example, if we're talking just strictly of stability, then graphite is more stable than diamond. And so the driving force is diamond should decompose into graphite. Is that going to happen in your life? No, it's not. The reason it's not going to happen is because the reaction is so slow kinetically. And so diamonds are stable. Diamonds are stable, but we don't say it's stable because it's not really stable. Graphite's more stable. And so we call it metastable. Diamond is metastable, meaning that, okay, it's stable enough. It's like a stick of dynamite. A stick of dynamite is metastable. You know, if you grab this stick of dynamite, is it going to blow up in your hands? No. But we know the potential to blow up is there, right? It just needs that extra kick. Well, the same thing with diamond. It needs that extra kick. Actually, a much bigger kick than dynamite does, right? To get it to react. You have this experience all the time. Methane and O2, big driving force to form CO2 and water, right? But if I fill this room up with methane and oxygen, I don't have to worry because it's a metastable mixture. The thermodynamic driving force is there. If I light a match, then we're in trouble, right? But as long as nobody lights a match and there are no hot surfaces around, then we're okay. And so we're looking at chemical reactions in a lot more detail in Chem 1B. And so this is why I want to review Chem 1A first before we do, that way you qualitatively have an idea of what should happen, and then in Chem 1B we're going to do some calculations to see. All right? Okay, so the first type of reaction is going to be metathesis, and so let's take a break here and then we'll start with that.